First of all, let me thank the organizers of seminar of numerical analysis for letting us organize this talk during the seminar. So thank you. Secondly, let me introduce myself. I'm Martin, a PhD student from mathematical modeling here at Charles University and the president of SIAM Student Chapter Prague, which is a student society that's organizing this lecture. If you want to know more about us, just Google SIAM Charles University, you'll find our web pages. Briefly, we organize talks like this, seminars, courses for younger students of LaTeX or Phoenix, and we are part of a greater organization, international organization SIAM, which means Society for Industrial and Applied Mathematics, which does this, I dare say, similar things as we do, but in much greater scale. They have the big conferences, journals, and so on. And this actually brings us, as we'll see in a minute, to the third and most important point of today, and that's our speaker. So I have the pleasure and honor to welcome here Professor Ridgway Scott, who will talk about modern approach to simulating flight. Ridgway Scott got his PhD at MIT. Later, he worked at University of Michigan, where he got his professorship, University of Houston, Penn State University, University of Chicago. He worked in, I dare say, nearly infinitely many fields, ranging from parallel computations to computational chemistry to nuclear engineering. And so I won't talk about everything, just a brief summary of the points that I think I roughly understand, at least the names. So first of all, he has been working a lot with a finite element method, which is arguably the most commonly used numerical method for solving partial differential equations. He wrote a book about it with Susan Brenner. It's called The Mathematical Theory of Finite Element Methods. It's a great book on the topic, so if you are interested in finite elements, go read it. He even has some elements named after him, Scott Fogelius elements. So he left a noticeable footprint in this field. He also left a footprint in the Phoenix project that I've mentioned that we work with. It's a software for solving PDEs, often used at Charles University. He is one of the co-founders of this software. He wrote a book about it as well. And since I mentioned that we are part of SIAM, he cooperated with SIAM as well. He, for instance, has been an editor of certain journals, so to name just those from SIAM, it's SIAM Journal for Numerical Analysis and SIAM Review. So I believe that these charts of Professor Scott's CV do not show that he is just a knowledgeable person, but that he also has quite interesting overlaps with what we do here at Charles University. So I'm really looking forward to the lecture. Speaking of the lecture, it's meant to be informal, so you are encouraged to ask questions even during the talk. And if you don't want during the talk, you can ask afterwards. If you want to ask during the talk and you are in this room, just raise your hand. If you are online here on Zoom, click the raise hand button. And if the speaker sees the raised hand, he'll ask you what's your question. And that's everything from me. So I think it's time for simulating flight. So Professor, if you are ready, the floor is yours.
Thank you very much. Thank you for the very extensive introduction. I appreciate all those nice thoughts. I am indeed a proud member of SIAM for many, many years, and I'm therefore very pleased to be giving a talk to a student SIAM group like yours. So I want to talk about a modern approach to simulating flight, and let me explain a little bit about what I mean by that. Well, first of all, let me talk about why do we care? Why do we care about this? Well, you probably have heard about the 737 MAX disasters, the two flights that crashed, and subsequent revelations indicated that there is not much use of computational simulation in aerodynamics in airplane design today, and it's not in the critical path of airplane design today. So that's something that needs to be fixed. And on a more positive note, there's an opportunity to do this with new startups who are proposing new kinds of airplanes, many of them electric airplanes, and many with completely different kind of applications. In fact, there's one that I refer to as a ground effect vehicle that's not exactly a plane because it doesn't get high enough off the ground. It can be considered something that, say, our FAA would require certification. Lots of things going on in new aircraft, and so we need to get computational simulation of fluid flow more into the critical path of this airplane design. And the new theory of flight, which I'll talk about, makes critical behavior computable. So we'll get to that. So let's do a short history of flight. Of course, Leonardo da Vinci was very interested in flight. And more mathematically, D'Alembert in 1752 raised what is known as the potential flow paradox, or more commonly, D'Alembert's paradox. So I want to start with that. Subsequent to that, Navier and then Stokes gave us what are now called the Navier-Stokes equations, which we sort of take for granted. But there's an interesting controversy about boundary conditions with both D'Alembert's theory, Navier, and Stokes. So we'll talk a little bit about that. One of the big waypoints in fluid flow history is the experiments of Reynolds, who essentially discovered turbulence and explained turbulence. Despite not understanding turbulence, the Wright brothers were able to get a plane to fly. There is some conjecture that it never really got out of what's called ground effect. So that's an interesting waypoint. In the mathematical theory, a major waypoint was the work of Sarin in the late 1950s, where he rediscovered or described what he called the Reynolds-Orr stability theory. And we'll think of it as it's a two-edged sword, so we'll think of it as an instability theory. Despite that being commonly known in certain mathematical circles in, say, the 1960s, Chandrasekhar, a famous astrophysicist, by the way, also professor of University of Chicago, which is, of course, why I'm mentioning him, wrote a famous book on fluid dynamical stability theory. And he used a theory called linear stability theory, which I will talk about, which is quite different from the Reynolds-Orr stability or instability theory. Reynolds, it's the Reynolds of the Reynolds turbulence experiment. So it's over 100 years ago that this was enunciated. I can actually read it in the work of Reynolds. I've read Orr's paper. I can't quite understand it the way Sarin may have, but I trust Sarin's description of it as the Reynolds-Orr stability or instability theory. So finally, down to the last one on the list, the new theory of flight that's proposed by Klaus Johnson and co-workers. And that's what I want to focus on today. But let me back up and talk about potential flow, what D'Alembert observed. So potential flow is a solution of the Euler equation. So Euler preceded D'Alembert and had written down fluid flow equations, where viscosity did not appear. So it was a very rudimentary set of equations. And D'Alembert realized that you could have what's called a potential flow solution. And the velocity of the flow is given by the gradient of the potential. And that potential is harmonic. And it has the normal derivative equal to 0 on the boundary. And that gives you this very pretty picture here. This is flow around a cylinder, potential flow around a cylinder, and that's where the paradox lies. So what was missing in Euler and D'Alembert's time are boundary conditions. Navier proposed boundary conditions. Remember, Navier came before Stokes. Navier proposed that the shear stress on the boundary should be proportional to the tangential velocity. So he said there would be a coefficient of friction. And when you look into it carefully, as we've done recently, you see that to get the potential flow solution around a cylinder with the Navier-Stokes equations, you have to take that friction coefficient to be negative. So a negative friction, which is a little bit of a concern physically. So it means an active wall that pushes on the fluid. And then Stokes later said, he was asked actually to adjudicate somehow, is Navier's boundary condition correct, or should you have something stronger, namely no slip? And he said, yeah, we're going to go with no slip. And that means taking a friction that's infinite. Okay, so that caused a fair amount of confusion because really Navier's boundary condition are more physically relevant. Okay, so let's go back to these pretty pictures. Here on the left, we have potential flow. This is actually the potential for the cylinder. So it's very simple. You can see how D'Alembert was able to understand all of this. And on the right, we have the Navier-Stokes equations with the Navier slip coefficient beta equal to 2. Now, I said that it's been shown that the potential flow is a solution with beta equal to -2. And you can see quite strong differences. So in particular with potential flow, as is obvious from the simple algebraic expression, the flow fore and aft is symmetric. There's this fore and aft symmetry, whereas that is broken here when you put a little bit of friction. So the fast flowing region moves a little bit downstream. Okay, but what is D'Alembert's paradox? D'Alembert's paradox said that the drag on the cylinder is 0. So the drag is a force on the cylinder, and he realized that that was something that contradictory. That common experience said there is a drag on a so-called blunt object, and so something must be wrong here. So as we've seen through the computations, if you break that fore and aft symmetry, things look plausibly different. And so here again on the left is potential flow with drag 0. Here is the Navier-Stokes solution on the right. And now let's ask the question, what's the drag here? So we'll come to that. So here it is. Here's the table of drag coefficients for different Reynolds numbers. That represents the speed at which the fluid is flowing, and for different friction coefficients. And finally, the Stokes no-slip condition, which is essentially beta equal to infinity. And we see that, for example, if the friction coefficient is very small, you get very little drag. And so, and of course, if beta were -2, then you would get no drag at all. So there is definitely a need here to have some sort of friction. But once you get a little bit more friction, the coefficient goes to what looks like an asymptote. So what we're measuring here is called the drag coefficient. So this drag coefficient can be defined in terms of this integral. So it's just the symmetric gradient of the velocity times the viscosity minus the pressure, and you've got a directional vector chi, which is 1, 0 for drag. So that means it's looking at things going in the direction of the flow, or 0, 1 for lift, meaning you're looking perpendicular to the flow direction. The drag force itself is proportional to u squared divided the speed divided by rho. Rho is the density, and this is the drag coefficient that was defined by that integral. So the term that is multiplied by viscosity here is called the viscous drag, and then the rest is the pressure drag. So it turns out drag and lift are mostly determined by pressure as long as the viscosity is small enough. And here's some data. So this is taken from a very interesting book, Incompressible Flow by Panton, which is available on the web. And this is data compiled by Panton from many different experiments. And this is the drag coefficient on this axis as a function of the speed of flow, the Reynolds number, as defined by this expression. And so it's inversely proportional to the viscosity and proportional to the velocity. And these red dots are our computed numbers at 4 different Reynolds numbers. And this is remarkable to me, to have computational data that matches the experiments that well. Now you might ask, well, why didn't we go further? Well, the computation becomes harder and harder the faster the flow is. That's one thing. But maybe more importantly is that, let's see, somewhere around here, the flow becomes unsteady. Flow past the cylinder becomes unsteady. It develops what's known as a vortex street, and it can become turbulent. We're not quite sure what turbulence means these days, but certainly it could become unstable, and different kinds of flows could be oscillating around some mean flow. So beyond about here, Reynolds number 1,000, we have to be more careful. Even at Reynolds number 1,000, I would say we have to be careful about what sort of turbulence or instabilities we're talking about, and what sort of averaging we should be doing. Okay, but up to that point, we match the experimental data remarkably well. Okay, so that puts D'Alembert's paradox to rest. He just didn't know about boundary conditions properly. And so now let's go on to the new theory of flight. So in this new theory of flight, what they propose is that the flight can be explained as potential flow augmented with some sort of instabilities caused by rotational vortices. Okay, so I'm going to modify that slightly. I'm going to say we're going to take, instead of potential flow, we're going to take Navier friction boundary conditions, and we're going to look at a specific kind of instability, Reynolds or kinetic instability. So most of the lecture is going to be talking about what are Reynolds or instabilities, and what are the standard linear instabilities, and how do they relate, and how do they match with what is seen experimentally and computationally. So what Johnson and co-workers found computationally is this picture. This is a cylinder, and fluid flow is coming in from the left here, and then it goes over the cylinder and is pretty smooth going over the cylinder. But when it gets to the rear of the cylinder, it develops these vortices, which are in the direction of the fluid flow and rotating. These are rotating vortices. Okay, so that's what they observed. And it's that the main points are that instabilities occur at the leading edge, at the trailing edge, not the leading edge. You might have thought the instabilities would start when the fluid flow hits the cylinder, but no, it goes smoothly over the cylinder until it gets to the very back end. And that's where the instabilities seem to come alive. And so we'll look at that, look at instabilities and see if they appear to occur at the trailing edge. And we'll show that this Reynolds or kinetic instability theory gives a precise mathematical way to describe those. And this conventional linear stability analysis can fail completely. Okay, just a little bit about those two. So one difference is that linear stability theory or instability theory predicts instability at a particular Reynolds number, whereas this newer kind of a really older theory predicts instability above a given Reynolds number. And then higher you go in Reynolds number, there can be a larger and larger space of possible instabilities. So let's take a look at that. So finally, we're done with talking, and now we get down to equations. Okay, so here's the fine print. So these are the Navier-Stokes equations. The time derivative of the flow is balanced by a viscous term, a nonlinear term, so-called momentum term, the pressure, and with boundary conditions. So let's talk about instabilities. What would that mean? So let's suppose there's another solution, call it W, and we're interested in a perturbation. So we want to think of U minus W at the initial time being a slightly different function V. So then what we can do is we can do what's familiar in variational theory. We multiply this equation by a test function. We integrate over the domain. We integrate by parts as appropriate. And what we can see is that after a lot of terms canceling, that we can have a growing solution starting with a function V, if and only if this expression on the left is sufficiently negative that it's the minus it is bigger than this viscous term. Here's how that's derived. So you take a solution W of the Navier-Stokes equations with slightly different initial conditions, and we pose V as the difference of U minus W. So that's the perturbation term. We can write down an equation for V. So it looks a little bit like Navier-Stokes, except that the nonlinear term, of course, is more complicated. And we can simplify that nonlinear term by just some algebraic manipulation. So it becomes U dot the gradient of the perturbation plus the perturbation dot the gradient of U minus a quadratic term. This becomes the full equation for V. We multiply by V, integrate over omega, integrate by parts, and this is what we get. Here, the C is the well-known trilinear form for Navier-Stokes. So it's this standard nonlinear term from Navier-Stokes dot a third vector valued function. And this has 3 terms, so we get 3 terms here. But there are some identities for this trilinear form that are well known. And with that, there is a lot of cancellation. In particular, you can see that this one, C of VUV, this one here, well, so first of all, those two are going to cancel, and we're left with C of VUV, and that remaining term is this expression, which appears initially to be non-symmetric, but here's a little exercise in mechanics to show that this symmetric expression involving the gradient of U is actually equal to the expression with just the symmetric part of gradient of U. So the strain associated with U, this is the symmetric part of the strain. So that's a little exercise to prove, or it's in my book on Phoenix. So what we find is this: the time rate of change of the perturbation is given precisely by the kinetic energy with a missing, there's a missing viscosity nu there. Maybe I've divided out here. I apologize. I've divided out by nu, and I've got the Reynolds number here. So my apologies. So what this means is that the perturbation will grow, its kinetic energy will grow if the expression on the right is positive. Well, this one's always negative, but this could be of any sign. So this could be bigger than this. And when would that happen? Well, so what we're asking is, when is this term bigger than this term? Well, that's a question we can raise. So let's just divide one by the other, and we get an expression here, and we say, how low can you go? What's the minimum of that expression? And if you get something less than -1, then this term dominates that term. So let's focus on this quadratic, this quotient here. Looks like a Rayleigh quotient. It corresponds to an eigenvalue problem. And let's ask when that eigenvalue is less than -1. So let's call this Rayleigh quotient L of V. It's a functional, it's not a linear functional, but it's a functional. And so if L is less than 1 for some V, then that means the perturbation will grow in time, and you can show it grows exponentially in time. If you have n eigenvalues less than -1, then there's a space of dimension n of unstable modes that will grow exponentially, spanned by the corresponding eigenvectors. And so the neighborhood of this space, because of this being a continuous functional on H1, corresponds to unstable flow. So this is quite a different picture from the standard linear instability theory, which I'll come to shortly. This says that there's this sort of bulk region in Sobolev space, which leads to instabilities. Okay, so what is the linear instability theory? The linear instability theory starts with the same equation for the perturbation, but drops the nonlinear term, the v dot grad v term. And it asks the question, could it be that there is an exponentially growing solution of this form? So we're looking for a special solution of this equation of this form. And note that this just grows in time, and the actual flow field does not change. Let me just stop and go back to the original equations or even these equations. So it turns out that quadratic term doesn't really matter when you're talking about small perturbations. So we can just look at this and say, there could be exponential solutions of this form, or there could be other solutions of this form. There could be solutions which grow in time, but change shape, change flow patterns as time evolves. So this is a very specialized assumption. That's the linear instability theory, very specialized assumption. We will see that that's quite different. So if you put in this ansatz to this equation, what you get is the exponential term comes out, and you get an equation which is an eigenvalue problem for the spatial velocity v naught that would be constant in that exponential growth. Unfortunately, this eigenvalue problem is not symmetric. It can be defective, and it may not have any solution at all. In particular, for one flow problem, you can show that there are no such eigenvalues for that flow problem. If it does have an eigenvalue, then it's not hard to show that there will be an eigenvalue for this Reynolds-Orr theory less than -1 minus mu. So if there's a positive eigenvalue here, which would lead to exponential growth, then there'll definitely be a Reynolds-Orr instability that has preceded it. So the Reynolds-Orr theory is more general than the linear instability theory. Okay, we do expect this thing to have a negative sign because we are talking about incompressible flow, and the trace then of the strain is 0. So it will have a positive term and a positive eigenvalue, a negative eigenvalue. And so this can definitely be negative as well as positive. And so let's consider a test case to see how this all works. So Couette flow, I'll describe that in a second. The first thing to know is that linear analysis says there are no instabilities. And this is actually a rigorous mathematical theorem. It's not easy to prove, but it has been proved. So Couette flow is the following. You have two plates moving parallel like this, and the flow in between them is a simple laminar profile that's proportional to the y variable, which is this variable here, and proportional to the speed u, and divided by the height here, which is 2h. So we take that as, and this, it turns out, is a solution of the Navier-Stokes equations for all speeds u, all Reynolds numbers. So you can check that out. That's a good exercise to make sure you believe that is a solution of the Navier-Stokes equations if you haven't done that before. And then you can read that paper to see that, in fact, it is linearly stable for all speeds. Okay, so that's Couette flow. And Les asked, what's the most unstable mode for Couette flow? Well, it looks like this. So you might ask, why didn't people know this before? Well, the answer is it wasn't so easy to compute. Whereas today with Phoenix, this is a relatively easy computation to do. And I have no idea what it means. So at the top, the flow is going to the right. At the bottom, it's going to the left. And this instability is 0 top and bottom. And it looks like it's going in the wrong direction. That's all I can say. I don't know quite what it means. But that's what it is on a domain of this length. Okay, and you can ask, how does it evolve in time? So we know that it's going to grow exponentially in time. That's a theorem. But we don't really know what's going to happen after that. And what appears to happen is that it grows, if the Reynolds number is high enough. It grows, and then it saturates, and then it decays. So that seems to be saying that the perturbation goes away eventually. And as you increase the Reynolds number, it grows higher, grows more, and then decreases, but the decrease is not monotonic, which is interesting. And you can go to even larger Reynolds numbers here, and you see more or less the same thing. So there's even greater growth. I've gone up to 100,000. You see a lot of oscillations as it decays, but in all the cases that I found, every perturbation eventually decays. So I couldn't find any perturbations that just continued on indefinitely. And you can look at the detail of this. So you can ask at what time for different Reynolds numbers, what time is the maximum. So that grows a little bit. You can say how big is the amplitude, that grows even more. And maybe the most important thing is the time of persistence. That is, how long does it take to get from whatever the initial perturbation is to where eventually it's below that, and that grows the most. So the persistence time is growing most strongly in terms of Reynolds number. And here's how it looks in time. So this is a sort of movie, a still version of a movie. So here's our initial perturbation at t0. Here's t equal to 1/2. So you can see that these ridge lines have deformed in some way. They deform even more half time later. They've turned. They're getting smaller here, and the scales are changing here, and eventually they get to be turned completely around and stretched in the opposite direction after 4 time units. This is at Reynolds number 1600. So the decay is complicated, and yet the evolution is complicated. So the perturbation starts out one way, sort of deforms, and then turns the other way, and is of course decaying in magnitude as given by these numbers here. So the amplitude, by these, you have to look at these. So this is how it's decaying in time. I guess we could go, here would be 4 time units for this bottom one. This is the blue one that I just showed you. And here's the last time picture here. And that's how much it's decayed. Okay. So what we're seeing is the world is divided into stable and unstable perturbations. And we start with an unstable perturbation. It seems to become even more unstable, but eventually becomes stable as time evolves. One paper raised this intriguing question about, could you have an instability that became persistent, that just kept wandering around in the unstable region? So far, I haven't found it. I did think I had found it at one point for one of the large Reynolds number flows. And I was very excited because I thought it might involve a Nobel Prize, but then I realized that I needed to refine the mesh. So I refined the mesh and that went away. So in every case, all my instabilities eventually decayed. So we haven't found this persistent instability, but maybe there is one out there. Okay, just a point of reflection. Why was this missed for so long? Well, there are various answers you can give, but maybe the most important answer is just that people couldn't compute them. And if you can't compute it, you don't know what's going to happen. And so I think it's the evolution of computational power and software power that has really been the answer for this. But let's look back at the history of PDEs a little bit. Of course, differential equations went back to derivatives, Leibniz and Newton. Euler wrote down the inviscid flow equations about the same time that complex numbers were established. So you know how primitive life was in mathematics at that time, because complex numbers were just becoming established. Later, Dirichlet came along and thought differently about differential equations from the way Euler did. So he established his variational principle. Dirichlet lived about the same time as Navier and Stokes. And then Dirichlet's ideas became more refined in functional analysis, Banach and Hilbert. And the concept of duality was established, which is absolutely crucial for understanding equations like shock equations, conservation laws. And then a next major waypoint was the development of the variational approach for PDEs by Jacques-Louis Lyons and Sarin and many other people. And so we are in this trajectory in this lecture. We understand the variational approach and we kind of naturally take that approach. And when you do that, you get to the Reynolds-Orr instability theory very quickly. Whereas Chandrasekhar, who's still contemporary with this group, used Euler's approach to PDEs. So I think that helps to understand why this linear instability theory persists even today. Okay, there's a lot you can say about the linear instability theory, but maybe I'll skip that in the interest of time and just go back to questions about why this matters. Okay. Well, as I said, computational simulation in aerodynamics is not in the critical path of airplane design today. Stall prediction is beyond the capability of most codes. Not the codes developed by Johnson and his coworkers, but most codes adopted by Boeing, NASA, Airbus, and others, can't predict stall. Stall is what happens when an airplane tilts too high up and it loses lift and it falls straight to the ground. And okay, so that happens. Ask any pilot, have you ever had stall? And I think at least many commercial pilots or military pilots would have said, yes, we've experienced stall, it's very scary. The trick is, how do you do stall recovery? Well, if you can't predict stall, you can't predict stall recovery. So this is just something outside the range of most codes today. And the 737 MAX, the Boeing 737 MAX, was considered likely to stall. If you don't know that story, it's easy to look up on the web. They put on new engines. The engines had to be moved forward because they were bigger, and they worried that it was going to cause it to tip up. And so they built a system called MCAS. It was an AI system which would attempt to tell when the plane was tilting up too much. And it failed fatally and caused 2 crashes, killing hundreds of people. And this all happened because we weren't using computational simulation to model aircraft behavior, in particular stall and stall recovery. And the new theory of flight says critical behavior is computable. It says we can look at instabilities. We now understand how to create understand or compute the instabilities around anything, a cylinder, an airplane, and that gives us a good understanding of what to expect from computational flows, which may be turbulent, but at least they're more realistic than the standard flow simulations done today. So here's what those flow simulations look like. So we get this very complicated flow, but it's very repeatable computationally. But let's ask, can we actually, we've talked about the Couette flow, can we predict this sort of behavior? Do you see instabilities behind the cylinder? And the answer is yes. This is what those computations look like. This is work done with Ingeborg Gerda at Simula. So yes, this is the most unstable mode behind the cylinder. And in fact, it occurs downstream. The fluid flow is going this way, and the instability does not start up until you're past the cylinder. And in 3 dimensions, you do see this alternation of modes going one direction and then rotating one direction and then rotating the other direction. So yes, and at higher Reynolds numbers, there are more and more instabilities. Here's one of the next ones where you see this flow going around and converging. So there are many, many instabilities for flow around a cylinder that can lead to very complicated flow patterns. Okay, so this leads to a new approach to turbulence, possibly. I studied turbulence many years ago via stochastic PDEs, as did many, many people. So using stochastic PDEs to model turbulence has a long history. What it says is that you can think of the turbulence as random, blah, blah, blah. You can do a lot of math. My opinion is, as someone who was heavily involved with it some years ago, this approach has not been a complete success. Maybe not a total failure, but certainly not something to keep working on. Now, I will say that turbulence may be multifaceted, like cancer. So you can't say turbulence is just one thing, and one explanation is not necessarily going to work for everything. But we have seen one type of turbulence, laminar flow perturbed by instabilities in Couette flow. So you get turbulent bursts, instabilities that grow and decay, and turbulent bursts, you can look it up. This is a commonly observed thing. And in fact, that was what Reynolds saw in his pipe experiments. He would get laminar flow at a certain Reynolds number, and then a bus would go by his laboratory outside in the road, and So that would cause it to shake, and you'd get this turbulence, and it would flow on down the pipe, and then it would reestablish steady flow after that. So that's what a turbulent burst is. I've not seen persistent instabilities, but maybe they exist. It's an interesting question what this is, which we'll get to real soon, we hope, to explain, is that a persistent instability or what? Here are some conclusions. So the new theory of flight holds promise to change qualitatively fluid flow simulation, allowing you to model things like stall. So you can be able to use computational simulation to optimize designs and assess deficiencies. Let me just say this is completely different on the structural side of aircraft design. If you look at how a wing is built, you see that it is, from a structural point of view, been highly optimized, and wings don't break. But they're computationally designed. Of course, they're flown in a test by a test pilot, but they are really designed computationally, whereas the wings are not. And that's what I'm trying to change. Okay, so you can improve performance of all kinds of vehicles, including possibly ground effect vehicles. That could be very effective. I say propulsion systems here, by which I mean jet engines or electric turbines. They're a little bit more complex because the fluid flow is compressible, so we have to consider that situation. Energy generation, such as wind turbines, and even medical treatments. My colleague Ingeborg has been looking at instabilities in blood vessels, and where she relates the existence of instabilities to possible medical issues. Okay, I also think that this gives us a new way to think about turbulence, which would be very useful. We might even be able to have more realistic simulators for pilot training so that we could give a test pilot the ability to go into a simulator and actually see if the plane stalls, how likely it is to stall, how hard it is to recover from the stall with a truly realistic flight simulator. We don't have any of that today. And finally, wouldn't it be nice if we could save a lot of money by doing at least a lot of this certification of aircraft computationally? One of the biggest barriers to developing new airplanes today is the cost of certification. Okay, those are some possible new things that can be done, but there are a lot of open questions still. So Couette flow on a longer domain looks like this. So it looks like what's happening as the domain gets longer and longer is that you get something that's spatially periodic. Is that true? Is there, if you pose a periodic problem with the right period, do you get a periodic solution that looks like this? That's not, I don't think, that difficult to do, but hasn't been done. The same question for flow past the cylinder, except now we're asking about periodicity in the cylinder direction. So we're asking in periodicity in this direction. We haven't done that calculate. I mean, this is tempting, but not a proof. And there are other kinds of flow in a pipe, flow in a channel. Couette flow was really first done by Couette in rotating cylinders. So you have one cylinder inside another and the outside is rotating. That's the real Couette flow, more complicated, but certainly feasible to study. Okay, let me stop at this point and say thank you to a whole bunch of people. Of course, most importantly, my colleague Ingeborg, who's done most of the computational work, I should say, and much of the other work as well. But many other people, Patrick Farrell, Matt Knepley, Matt Larson, Leo Rebholz, Nick Trefethen, contributed early on to my understanding of this. And maybe most importantly was a book by Johan Hoffman and Klaus Johnson that really got me involved in this in a serious way. Trying to understand what they were saying led me to this understanding of Reynolds-Orr instability theory and the rest of the story. So with that, let me stop and just give some references. Here is this very important book by Johnson and Hoffman, and let me open the floor for questions. Thank you.